Hello everyone, thanks for watching this presentation. My name is Qinshan Chu. I am a research scientist at Facebook, and this work has been done when I was the graduate student and working with my colleagues and my advisor, Dr. Panda, at the Ohio State University. So the paper is Dynamic Kernel Fusion for bulk non-contiguous data transfer on GPU clusters. So today I will talk about briefly about the introduction of the non-contiguous data transfer on the GPU cluster. What's the problems and what's the solution I'm trying to propose in this paper? And with the proposed design, I also share some performance numbers. Then I will conclude the talk. So first of all, if you look at the modern HPC systems, now you can see this kind of trend. We call it heterogeneous. By that I mean that you are not just using multiple many core processors like the CPUs. Nowadays, you can see a lot of accelerators being deployed in the HPC systems. For example, the NVIDIA GPUs or AMD GPUs and more. And in order to put all these powerful GPU systems together, you have to use a high performance interconnects such as InfiniBand to connect these GPU nodes, and sometimes you may also have the storage devices. So if you look at the bottom, if you look at the top 500 supercomputers, you can see that these top supercomputers are actually powered by thousands of GPUs right now, and maybe you will see more such systems in the next few years. Let's tell us like how important the GPU is right now in the HPC community and for a lot of different applications. So application also trying to utilize or accelerated by the GPU, and in the legacy HPC application, non-contiguous data transfer is one very commonly used communication pattern. Some people also refer it to hello exchange or phase exchange or 2D, 3D domain decomposition. So a key idea is basically like if you're trying to distribute your workload, you distribute your data to different GPUs, at some point you have to synchronize the results, right? And this is where you have to exchange the boundary data, which is not contiguous in the memory. For example, these columns or these domains between the GPUs. And bulk communication happens because there are multiple GPUs. You have to perform the communication between GPU for different domain, for different columns, for example. So you may have multiple communication back to back, and they are all non-contiguous data. So that's the key of trying to scenario we're trying to address in this paper, the non-contiguous data transfer for bulk communication. And right now, it's already a lot of GPU-based approaches existing, especially in the MPI, the message passing interface. It defines we call it derived data type, so you can use that to represent your non-contiguous data. And there are many ways, many optimization for the GPU-driven packing and unpacking routine. Packing means that you want to pack the non-contiguous data to a contiguous buffer, then you can send it out. And when you receive it, you have to unpack it back to the non-contiguous buffers. So we have these routines, and there are many ways to optimize it. Roughly, there are two approaches. First, I call it synchronous, which means you optimize your kernels. You look at this paper, and there are more. I'll talk about how you optimize your kernel, GPU kernel, to perform the packing and unpacking on GPU. And you have to do explicit synchronization between CPU and GPU. Here's example I'm showing here. Like your CPU, you launch your kernel, you will see some penalty, some overhead, and GPU can execute the packing your optimized kernel. Then once you finish, this is where we perform the synchronization. So basically CPU is kind of idle here, right? And once it's finished, you perform your communication like send or receive, and you do this one by one. So this is synchronized manner. So if we can do synchronously like the second one, we kind of delay the CPU GPU synchronization to get more overlap. So the flow will look like this. You still have this overhead, of course, and you launch multiple packing kernels, for example. Then as soon as possible, if there are many, because for bound communication, there will be multiple non-contiguous data going to be transferred. So you have multiple pack kernel. So if the kernel is long enough, you can expect some overlap between this packing operation, and sometimes also between the GPU and the communication on CPU. So CPU will be responsible for talking to your network adapter to perform the communication. So you expect some benefit using asynchronous, but unfortunately there's still some performance issues. We found that even GPU-driven packing unpacking is very fast, much faster than using CPU, but comes with high penalty. And the penalty is actually coming from the kernel launch overhead I just mentioned. Sometimes it always the optimized kernel. So here's example I'm trying to show you. We're using two different workload, very famous application like Spectrum3D and Milk. So we profile these packing kernels, optimized packing kernel on the GPU using different GPU architectures from K40s to now the recent one, the Volta GPU, NVIDIA Volta GPUs, and you can see that packing is very fast, take like 10 microseconds, or sometimes only for different workload it could be just 2 microseconds. But if you look at the launch overheads, it's like a constant, like it's usually 5 to 10 microseconds, sometimes faster, sometimes is slower. But in overall, you can see that we actually spend more time on setting up a launcher kernel and run it. I think this is known issues or known behavior if you are familiar with CUDA programming. So usually the best practice of CUDA programming will be like trying to put more work in a single kernel, so you can hide this kind of overhead, right? But in packing unpacking is not the case, because packing unpacking is a very very simple operation. It's not the compute intensive operations, right? So it's very fast. So in this way, even we have this asynchronous approach I just mentioned, you don't get a benefit. You still lose the benefit here. So we can look at what's the impact here. Like you still have launch. You can launch multiple packing kernels, but because this packing is very fast, very small, and you still have this high overlap. So you can see that there's no way you can overlap this packing kernel. So you have very small or even zero overlap, and overall you don't get the benefit you expect. So your communication is still slow here. So in this paper, we're trying to resolve this. We're trying to see how can we minimize the overhead of launching kernel and still maintaining the high overlap between the communication and also between the packing unpacking operations. So the key goals are following. First, we're trying to hide or at least reduce the number of kernels we're going to launch for packing unpacking. And second, we're trying to better utilize the GPU memory and thread parallelism, so you can get some more overlap between these packing unpacking operations at least. Then we can see if we do it right, we can still overlap some packing unpacking operations and the bound communications, especially for the large messages. So we propose this design. We call it kernel fusion for GPU-driven MPI data type processing. So kernel fusion is not a new concept. It's been there for a while, but we have never tried to apply it for the non-contiguous data transfer. So here we're trying to see, first we propose to fuse the packing unpacking kernels, so you don't have to launch a kernel every time, right? Because we know the kernel is very fast, and because of we have this bound communication, this kind of property, this kind of behavior, so we can fuse the multiple packing unpacking. We delay this communication a little bit, but we fuse all together, so we can pay the penalty only once. Then we can try to utilize more GPU resource in this fused kernel, so we can also reduce the packing unpacking latency. So here's a example how it looks like. So the proposed one compared to asynchronous, you'll see that we may have a small gap here, small delay here, because we're trying to fuse a kernel, trying to figure out how many we're going to fuse. Then at some point, we fuse enough requests, so we launch a kernel. So you have to see this, experience this overhead at least once, right? Then you launch this fuse kernel. So as you can you can notice here is that this fuse kernel is actually as fast as packing one single buffer, right? But here actually we fuse all three together and pack it in one single kernel. We pack three kernels, three buffers, for example. That's because we can utilize more GPU resources here, put more thread to move the data for you. So there's also benefit from the very powerful GPU nowadays. Then if some packing or unpacking finish early, you can signal back immediately, and we don't want to wait until the kernel boundary. So this is second benefit we can have. So we propose these two main designs so you can get more overlap between this packing and unpacking, and also sometimes between the send and the operation and the packing. So you will expect some more benefit by using this kernel fusion design. So let's look at the framework. Here we simply introduce one more component called scheduler. This schedule will coordinate with the communication progress engine. This is running on CPU, and the kernel is running on GPU. So basically the idea is like your progress engine may have some send receive operations, but it requires packing unpacking. So we put this such request, talk to a scheduler, put the request in this request list or a queue. Then when we have enough data queued here, enough requests queued here, the schedule will launch one single kernel, and in this fuse kernel, it will be calling different functions like packing or unpacking for different buffers, right? And also the direct IPC. The direct IPC is another mechanism to perform a zero copy data movement for non-contiguous data. So I'm not going to detail, it's not in this paper. And you can imagine in the future this can be extended if we have different way to optimize this packing unpacking behavior. So if you look at this kernel, you will be looking like this. On the right, you launch a fuse kernel, you have multiple threads, maybe thousands of threads. We first do a partition. So after this partition, just a few a smaller thread group perform different operation. For example, some thread performing packing, some are performing unpacking or direct IPC, and we don't have to do a like global wise or grid wise synchronization. You can do this just group wise synchronization. And once this, for example, if this packing finish, it can just return back scheduler by simply update his request object. So the scheduler will know, okay, this packing is finished, for example. Then scheduler can work with the progress engine to complete the send receive operation. All right. So the key question is like when to launch a fuse kernel and how much data is enough to launch a fuse kernel. So here we're trying to discuss that you basically want to avoid underfuse, which is you launch kernel too early and you don't actually reduce the launching overhead, so you get the same penalty. Or also you don't want to overfuse, which means you delay too many communications, and you reduce overhead, but you lose the opportunity to overlap between your packing and the communication. So here I'm using this one example to show you what this looks like in the real world workload. So for different input size here, these are all non-contiguous buffers. Then we are using different threshold. Basically, which means we use the threshold. For example, 60 kilobyte means that, okay, if I have 16 kilobyte or more data fuse for packing or unpacking, then I'll launch the kernel immediately. Same thing for, so when you have higher threshold means you will fuse more data to launch one single kernel for it. And here, this part is what I mean the underfuse, which means your threshold is too low, so you don't fuse enough data, so you almost every time you almost launch a kernel for each buffers, or maybe just launch one kernel for 2 buffers, so it's not optimal. So your latency will still remain very high. And this point is the example of overfills, which means your threshold is very high, and you fuse too many data, and actually when the message gets larger, you actually have opportunity to overlap. You don't have to fuse everything for the best latency. You also want some overlap between the communication and the packing, so you don't want to go there. There's overfill. So in the example I'm showing here, the optimal threshold looks like is 512 kilobyte. And again, this depends on your system, depends on your workload. In this paper, we try to tune that for different system, different workload. But usually the threshold is around 256 kilobyte and 512 kilobyte. So we can dynamically fuse different numbers of kernel to avoid the launching overhead. So finally, let me share some performance evaluations. We did the evaluation on 2 kind of system. One is the Lassen system, is the Power 9 system. It has 4 voltage GPUs and connected by NVLink between CPU and GPU as well. And it's using dual rate Mellog's IBEDR. And in second system, the ABCI system in Japan, is the Intel Go Skylake system. And it also have 4 voltage GPUs, but the difference here is these GPUs are fully connected by the NVLink, and so it only have PCIe to connect CPU and GPU. So you can imagine there's different bandwidth between CPU, GPU, and between GPUs, and also using Mellog's IBEDR. And in this paper, we use application kernels, very common application kernels. We modify the DTT branch and to use GPU, and we also mimic the 3D decomposition workloads like the bulk send receive operation, similar to many applications you can see in HPC world. And here we use different real work workload, the pattern like NAS or Milk, SpectrumMPI, CN, and OC. So you can look at the paper and also look at the DT bench for more information. And the baseline, we are comparing our GPU sync that I just mentioned. You have optimized kernel, but you have do the synchronization explicitly, and you have a sync design. And one is in our earlier HPC paper, we have this CPU GPU hybrid version. Means sometimes you use CPU to do a packing unpacking, sometimes you use GPU. So all these were implemented in the MVP2 project, especially specifically in the MVP2 GDR library. So this has been powering a lot of application, also the top 500 clusters. Please check out the website for more details. And first, we look at the breakdown, see what happened here. We use Milk workload here on ABCI, but I just want to share with you that you can see a similar trend in all kind of workload and different systems. So the key takeaway here is like using GPU async, you will see very high sync overhead like we have expected. And using async, you have a scheduling overhead, and because you delay the communication, so you can keep checking if the packing is finished or not using some CUDA API like CUDA event, record, CUDA event query, those kind of API. So you will add some overhead when you're trying to complete the communication. This is why you see some higher communication time here. And with the proposed design, you first thing is you have comparable packing unpacking time, maybe slightly higher sometimes because you have to do the partitioning, but it has significantly reduced the launching overhead here, and you have lower communication time. And this also translates to the different workload on the NVLink and InfiniBand system, multi-node, multiple send receive for Milk kernel, for SpectrumMPI, we see a significant speed up also compared to other MPI libraries. We have very significant speed up. This is on Lassen system, and CPU sometimes will perform better because using CPU you don't do the packing at all. You don't have those overhead. So it depends on different workload, different system. Please look at the paper for more details, evaluation. And to conclude the talk, we talk about the bulk non-contiguous data transfer. It's very common, and using GPU is very good, but it comes with very high overhead. So we propose a fusing kernel design to reduce such overhead and increase the GPU utilization and increase the overlap opportunities between the packing and unpacking operations. So all of this design will be made publicly available in the upcoming MIP2 GDI release. So please stay tuned and check out our website for more details. With that, let's thank you. If you have any questions, feel free to send us email and check out our project website. Thank you and goodbye.